starting recording. Recording is started. Okay, we have already talked about the insertion operation. Remember, insertion grows the tree from the root, not from the leaves. In B tree, and removal is also generalization of the remove operation on 233. If we have to remove from a leaf, the removal is simple. We just remove the element from the leaf, and it is simpler. But if we have to remove from an internal node, we have to be careful. If we have to remove from interior node, we have to replace that value with its in order predecessor or successor. In order predecessor or successor should be in a leaf. So we take out that successor or predecessor and put in place of that interior and the value in interior node. So we perform the removal from a leaf in turn. Okay, so removal from interior node also result in removal from a leaf, right? How we are gonna remove from a leaf? If the leaf is half full after more than half full after removal, we are done. But it becomes less than half full, then we have to perform some operations to correct that problem. And we have to perform a redistribution between the parent and sibling. How we are going to do that? We have an example here. If we have to remove 40, we have to find in order predecessor. In order predecessor is 39, right? We have to follow the left link and find the largest, which is 39. We move 39 in place of 40 and delete 39 from this place. And we are done since this node is more than half full, right? We replace 40 with in order predecessor. We have this situation and we are done. If we have to remove 18, 18 is at the left of 20, and when we search here, it is the more than largest, so we have to follow the rightmost link, and we find this leaf. 18 is at a leaf, so we can easily delete this 18, but after deletion, this node becomes less than half full, so we have to perform merge operation, merge with a sibling, and the value that splits this true node. So we have to merge these three pieces of information together. So we have only one item here, so we have to merge these three to have a single node. So we delete a node, and when you look at this parent, now the parent becomes less than half full, so we have to merge with its sibling, and the parent value. As you see, in here, we merge with the left sibling, right? This is half full. We are merging with the left sibling. We are merging with the right sibling, right? This is half full, and this is the right sibling. We can merge with the left sibling or right sibling. That's also a choice. You can do whatever you like. Similar to this thing, when you remove 40, you can replace 40 with predecessor, or you can replace with successor, right? When you replace with successor, right, 42 can be moved here and deleted from here. This becomes less than half full. We have to use left sibling root value and this value together, 32, 35, 38, 39, 42, and 46 together. And of course, all these values cannot fit in a node. So what we have to do is split these nodes. We can move 39 up, and this may be left sibling, this may be right sibling. This is one way. Another way is we can move 38 up. This is left sibling, and this is right sibling is also possible, since middle element is either 38 or 39 in this case, right? We cannot say this one is the middle element. So you have to be careful. This merge operation, after removal, we have to merge with these values has to merge. We may have 16 here as well, right? 16 would be here as well. In that case, 13, 15, 16, 17, and 20 may not fit in a node. So what we have to do is to move 16 to parent, and this is the left child, this is the right child of 16, right? So we perform a redistribution, not merge. As you see here, we said redistribution. We do not perform always merge operations. Sometimes we have to perform redistribution. Okay? So we have to merge this value. Remember, we have deleted 18 from here. So when we delete 18, 20 is the just one value, which is not satisfy the condition of the properties of the B tree. So we have to perform a redistribution. And since merging these four values into one node is possible, we perform that. And now the parent becomes less than half full. We have to merge with the right sibling, and we perform that. And tree becomes one last level in that case, right? In this B tree, all the operations, as you see, depends on the height of the tree. height of the tree is logarithmic. Of course, at each node we have to process several pieces of information, but that number is constant, which is order. Order is constant, so we can still consider the operations in a node to be a constant time operation. And since the height is logarithmic, the overall running time of B-tree operations is a logarithmic time operation. As I said before, when we store the values in a secondary storage, each node keeps a key value, which is the search key, and a value as address of the element that has this key value. So this, for example, for the student information, this key is the student ID number, and the value for all the values about the student, the name, address, phone number, GPA, the courses, the grades, etc., are stored here. We access that value by using this key index, right? The student number. So actually, each element that we store in here should be a key value pair. Here we should store key value pair. Here we should store key value pair. Value is an address, right? This address value points to the exact disk block that stores the whole information about the database entry. Actually, for the leaves, as you see, we do not store any child information. So we can store the value here, the key here, and the address for this key information can be stored in this child positions. But for the internal node, this is used for the next child, right? So for the leaves, we can use child indices, child references to store the position of the values, right? Since at leaf nodes, child pointers are not this waste of space, but it can be used for the address for the value itself. In B tree, B plus tree uses this idea. In B plus tree, the internal nodes keep the keys only and pointers to the children, but the leaves contain the keys and pointers to their corresponding values. Internal nodes contain keys and pointers to the children, as in B tree. But in this case, we keep all the values in the leaves. So the leaves keep the values, all the values. These are also leaves. Internal nodes repeat the values. As you see here, this is the actual value. It is repeated in the internal nodes. These are the internal nodes, right? We repeat. So this link, this subtree, contains all the values, including 5 until 22. This link, so this subtree contains all the values from 22 to including 22, of course, to this value. This value is not, so everything. Okay. So the values are repeated in internal nodes. The parent's value is repeated as the first value. And there are the number of keys and number of pointer children for a node is same. Remember, the order is number of children, and the number of values, number of keys, number of data elements is one less in B tree. In B plus tree, number of children and number of values are same number. So B plus tree has a little difference over B tree, and it makes the use of the data space in secondary memory more efficiently. So it is often used to store the database values in the database indexes, actually, in the secondary storage. Okay, next topic is the skip list. We are going to introduce the skip list today, and we are going to continue and finish the discussion tomorrow. So is there any question about B tree or B plus tree? Actually, the removal process of B tree, probably. Okay, there is no question, so I'm going to continue with skip list. Skip list is not a tree structure. It is a list structure, actually linked list structure, similar to linked list, but it doesn't have just one linked list, but we use several linked lists in skip lists. So it is skip lists. We have more than one list in skip lists. So we can use this data structure to implement navigable set or navigable map. Remember, in Java, both these are implemented by using red-black tree, but we can use skip list instead of red-black tree. Red-black tree is tree-based data structure, but skip list is a list-based data structure. Actually, the advantage of skip list is where you have several threads, and you need concurrent access to this skip list by using multiple threads. in that case, in tree set, using red-black tree, we have to lock the whole tree, and only one thread can access to red-black tree or tree set at a time. But on the other hand, for skip list, all the threads can access concurrently to skip list without locking the whole structure. So this concurrency and using multiple threads is not in the scope of this course, but still you should know that the skip list has advantage for concurrency, and it provides logarithmic operations for search, insert, and remove operations. But remember, the red-black tree has worst case logarithmic time, but skip list has worst case linear time, while the average running time is logarithmic, like in quicksort. In quicksort, the worst case quadratic and squared, but the average case was n log n, and it was the it is a very fast sorting algorithm, remember? Although the worst case is linear in skip list for all these operations, worst case is linear, still average case is logarithmic, and it is quite a fast algorithm to perform these operations. Quite a fast, actually, data structure for these operations. So you can prefer skip list because of this concurrency features and average case good running time. Okay. So in skip list, we have several lists, several linked lists actually. So we can consider it as list of linked lists. We have list of linked lists. So each element in the data structure is a part of several linked lists. Not only one linked list, but several linked lists. So as in here, for example, 20 is a part of this linked list. This is a linked list of 3 elements, including head. Maybe you can consider 4 elements, right? And part of a linked list of 10, 20, 30, 36, and 40. And also it's a part of a linked list that contains 5, 10, 15, 20, 25, 30, 35, etc. All the elements in this linked list, right? So 20 is a part of 3 linked lists. 30 is a part of 2 linked lists. 35 is part of just 1 linked list. Okay, so here we have 4 linked lists, 4 heads, as you see. Head we have several heads for several linked lists. So a node can have very number of forward links. For example, here 20 has 3 forward links, 35 has just 1 forward link, etc. We call a node to be level M node if it has M forward links. So 20 is level 3 node, 35 is level 1 node, 30 is level 2 node, etc. And as you see, 40 is level 4 node. And 4 is the level for this linked list, skip list actually. 4 level skip list, level 4 skip list, right? We have 4 skip lists. And we can say that half of the nodes, half of the elements are level 1. As you see here, almost half of the level elements, 5, 15, 25, etc. Almost half of them, 1, 2, 3, 4, 5 of them are level 1. 1, 2, 3 of them are level 2. 2 of them are level 3. And 1 of them is level 4, right? We can say that half of the elements are level 1. 25% are level 2. 12.5% are level 3, etc. So when you have this many elements, half of them are level 1. Half of the rest is level 2. Half of the rest is level 3. Half of the rest is level 4. Half of the rest is level 5, etc. So for a node, the probability of a node to be level 1 is 1/2. Probability of a node to be level 2 is 1/4. Probability of a node to be level 3 is 1/8, etc. 1/2, 1/2 square, 1/4, 1/2 cube, 1/8, etc., etc. 1/2 to the 4, 1/16, goes on and on as the levels are increased in the tree. Skip list actually, not in the tree. Okay. This is a level 4 skip list. And it is a good skip list actually. For example, remember, complete binary tree is a good binary tree, which has logarithmic height, right? Complete binary tree is a good binary tree. And this tree is a good this skip list is a good skip list. Why? Because every next element is level 1. In not level 1 nodes, elements, every next is level 2. Between not level 2, every next is level 3, etc. Okay, that's why it's a good skip list. It is like complete tree for binary trees. It's not necessary to be like that. For example, we may have something like this. A node here, which is head, a node here, which has the same, everything goes to here except the first skip list, and first skip list has all the elements. This is also possible. All of them are, all these are level 1, except just one node. This is possible. It is, probabilistically, it is not very probable, but possible. And this is the worst case skip list, actually. So, and it is not always possible, as I said. So, the skip list here is an ideal skip list. Most skip lists will not have exactly this structure, but the behavior will, average case behavior would be similar. Remember, average case behavior of all the trees are logarithmic, like complete binary tree, right? Average case behavior is similar to this ideal skip list. Again, this is ideal skip list. And how we are going to perform search operation. We start from the topmost linked list. We try to locate the element in this list. Actually, we have only one element, 40, and everything here is less than 40, everything here is greater than 40. And search begin with the highest level list, which has fewer elements. For example, to be able to search 35, we start with this link and follow the link at level 4. We get 40. 35 is less than 40. So we know that the value should be in this place. And we go one level down to level 3 link and try to locate 35. The first value is 20. 20 is smaller than 35, so we continue. We get to 40. 40 is larger. So the value 35 should be in between these two. So we go back to 20 and one level down to level 2 linked list and continue. 35 is greater, so we continue. 30 is less than 35, so we continue. 40 is more than 35, so we have only this place left. So we go one level, we go back to 30 and one level down. We follow this link and we found 35. If we are searching for 36, we said that 35 is smaller. We follow 40 is larger, and it was not like in this level 1 linked list, since everything is in level 1 linked list. So 36 is not in here, so 36 is not available. Okay. If we reach a value greater than our search target and we couldn't find it yet, we can decide that the value is not in the list, not in the skip list, like 36 is. So this is the search operation. We continue with the highest level and decrement the level one by one until 0, and find the node with the largest value that is less than or equal to target. And in that node, we continue with the one level down, etc., until we find a value that is equal to the target. If we found equal to target, of course, we exit the loop and announce the result. If we go through all the levels until the first level, and if the target is not in the first level as well, then we can say that the target is not in the data structure and announce the unsuccessful find operation. Okay. The performance is logarithmic, since in upper levels we have less number of nodes, and actually by comparing with 4D, we just get rid of half of the elements, this part, for example, and by comparing 20, half of the elements are discarded, this part. By comparing 30, half of the elements are discarded, etc. So it is like a binary search. You discard half of the elements after each level. So because first list search has fewest element, and every successful level has approximately half as many elements at the current list, this search performance is logarithmic, which is similar to binary search. Again, this logarithmic time is approximate logarithmic time, not worst case logarithmic time. As I said, the worst case would be similar to this one, and in this case you can search in the first level only, and it takes linear time anyway. So worst case is linear time, but the average case is logarithmic time. We can talk about insertion and deletion as well, but time is up, so I'm gonna stop here. Tomorrow I'm gonna talk about these insertion and deletion operations first, then I'm gonna talk about the exam questions. See you tomorrow. If you have a question, you can ask right now, of course. But other than that, we are going to continue tomorrow. Yes.
Have a nice day, sir.
Thank you.